Find the equation of the tangent line to the curve, y squared times the quantity of y squared minus 4 equals x squared times the quantity of x squared minus 5. That's quite a mouthful. It's got y very implicitly defined. To be able to isolate the y and define y explicitly would be very difficult and would look very ugly. It would probably need a computer and the equation would be a bit of a mess. So this one is easier to differentiate implicitly. So that's what we're going to do. So to get the tangent, what we really need is a point, which they've given us. How nice of them. So we have the point 0, -2. And now we just need the slope. And the slope is going to be equal to the derivative of y with respect to x, defined at 0, -2. So that's what I'm looking for right now. I'm looking for that derivative defined at 0, -2. So to find that, in fact, I'm going to write that bigger over here. And my goal is to find the dy dx defined at 0, -2. This is my goal. So let's put a box around it so we don't forget what we're looking for here. So I need to derive this, right? I need to use differentiation and find out what the derivative of dy dx is. So I'll use implicit differentiation. So step 1 is to differentiate both sides of the equation with respect to x. That with respect to x is very important because we're looking for dy dx, which means if we don't explicitly see the x, that means that we're dealing with the chain rule and a function of x. Remember that y is a function of x. Y is equal to some function of x. We don't have that function defined explicitly, but it is a function of x. So when I see something like y squared, that y is really my inside function, and I would do the derivative of that, the derivative of y squared in respect to x would be equal to the outside function times the derivative of the inside function. And the inside function is the y. So y is f of x. We just don't know what f of x exactly is. So to remember that y is a function of x, so we treat that like a chain rule with an inside function of y. All right, so the first step is to differentiate in terms of this. And after we get everything derived in terms of x, and the reason we do that is so that our step 2 will be to solve for dy dx. I have a little mistake on this step 1. It should be just d dx. We're taking the derivative of everything, including the not y's, into respect to x. Okay, so let's go ahead and start. So we have this equation. To differentiate this as it is, I would have to use product rule a couple times. It would probably get a little bit messy. You could definitely do it that way, but I think it might be easier to simplify it first by just distributing, because my exponents on both these parentheses are just 1. So I could easily just distribute, and then I'd just have 2 terms on each side with a power rule. So easy peasy. So let's do that. So let's just distribute first, and we get y to the 4th. So just getting rid of those parentheses. So there I just simplified first. Okay, the next thing I want to do is take d dx of both sides. Okay, so this is where I'm going to actually write out exactly what I'm going to do. So I'm going to do d dx of y to the 4th minus d dx of 4y squared equals d dx of x to the fourth minus d dx of 5x squared. No, you don't really need to break it up as much as I just did, but I just want to show each individual step, but you could just take d dx of the whole left side, like you could do it like this, would be acceptable as well, and just knowing that you can go term by term from there. At least one line that you're taking the derivative of both sides. All right, so from the right-hand side, it's much more direct. Hand side, both the functions that I have, x to the fourth and 5x squared, both those functions are explicitly defined in x. So when I take a derivative in respect to x, that's just going to be 4x cubed and 10x. So right side's easy. But the left-hand side takes a little bit more thought. So on the left-hand side, the first derivative I have is y to the fourth. In respect to x, with respect to x means that y is some inside function that I can kind of box off, and then my outside function is my variable to the fourth power. So like my y to the x is kind of like the u when we talked about chain rule. So this is really u to the fourth here. So I take the derivative of the inside function, the outside function with respect to the inside function, and then multiply it by the inside function. So that is, u to the fourth would just be 4u cubed, but our u is really y. And then I have to multiply it by the inside function, derivative of the inside function with respect to x. And the inside function is y. So again, y is my inside function. My outside function, I would differentiate and just do 8y times the derivative of the inside function with respect to x. So every time I take the derivative of a equation that's defined in y. Every time I see a y, I'm going to take a derivative of y because y is an inside function. So the derivative of y is just 1 times y, so that would be just dy dx. So I can write that this way. And everything else doesn't change, I just copy it down. So what I'm really looking to solve for is this dy dx. That's my variable. That's what I'm solving for. So I've already taken my derivative, and now I'm going on to step 2 to solve for dy dx. So we'll do step 1, we did in blue, to differentiate both sides with respect to x. So we found our d dx in blue. And now I'll use purple and we'll solve for dy dx. So our dy dx, we're just solving for this variable, just like you would good old-fashioned algebra, just like it was an x that you're solving for that piece. So to get it isolated, so we can solve for it, first I need to factor it. So I'm going to get it out of that, gather them together so that I can isolate it. So factoring it from both sides, factoring it from the left, and then divide both sides in order to isolate it. And this I can reduce a bit, simplify a bit. Let's see, I can take out a 2x from the numerator, and I can take out a 4y from the denominator, and simplify this, the 2 and 4 reduce. So I get a final derivative in terms of x and y. So my derivative, my slope will depend both on x and y. So I get 2x squared minus 5 over y squared minus 2. So to answer that original question of finding the slope of this line, because we need to find the line, that's really the original question. We need to find the slope defined at 0, negative 2. We're going to plug in we want to find dy dx with respect to the point 0, negative 2. That means we take the dx dy we have found and evaluate it at 0, negative 2. So plugging in 0 for x's, oh my, I'm sorry, I have a little mistake here. So I did not carry down the front of my fraction here. Dy dx is actually x times all this, and the denominator is 2y times all this. There we go. So now when I plug in, I get 0 for my x's, and negative 2 for my y's, which means I get 0 in the numerator, negative 4 times 4 minus 2 in denominator, or 0 for negative 8, which is just 0. So the slope of the line and we know the slope of when the slope is 0, that means I have a horizontal line at y equals some constant. That's always the formula. I could always go to the slope point slope form and plug in my slope, which we just found to be 0. Now we now know that equals 0. And our point 0, negative 2. And put that into point slope form. So we would get y minus negative 2 equals the slope times x minus 0. So I'd get y plus 2 equals 0, and then solving for y, I get y equals negative 2. And that is my tangent line. But since I see is y equals 0 is it's going to be a flat tangent line, a horizontal line, and I know horizontal lines always are in that form, I could just look at the y value and see, okay, I know my tangent line is horizontal going through that y value, so it must be y equals negative 2. So either way, you get the horizontal line of y equals negative 2, and that is our tangent line. Either way. So step 1 was to differentiate but with respect to x. Step 2 was to solve, and since this question actually asks us to find the tangent line, we find the dy dx defined at our given point. as our slope. So that's step 3. And then step 4 was to use point slope form or just the horizontal line to find the tangent line. So we don't necessarily have to use point slope form. We could have just used the point in the fact that it's a constant function. So I'll just say we'll use the point and slope, however you see fit.